Welcome to this explainer. Today, we're going to do something incredibly satisfying. We are going to build a comprehensive working module right from the ground up. But we aren't just going to plug things in and cross our fingers hoping for the best. No, we're going to completely connect the dots between the abstract software we write, the microscopic quantum physics happening deep inside our components, and the practical mathematics that keep the whole system from literally going up in smoke. So let's dive right into this.
Okay, here's our game plan for today. We'll systematically zoom in, starting with the software layer in the hardware hello world. Then we'll shrink way down to the atomic level to see how LEDs actually work. And finally, we'll run the numbers to prevent thermal runaway.
Now, you've probably heard this phrase before, but let's establish why it's absolutely crucial. This simple blinking configuration is foundational. It's basically the ultimate sanity check. By getting a single little light to blink, you are definitively validating that your development environment can successfully compile and upload instructions to your microcontroller. It's the proof that the bridge between your computer and your hardware is fully operational.
Part 1. The hardware hello world. Let's see exactly how we translate abstract C++ code into physical hardware action.
So our program architecture basically breaks down into two distinct phases. First up is void setup. This is a mandatory initialization that runs exactly once when the system boots up. Inside it, we use pin mode to declare our built-in LED as an output. This physically modifies the chip, telling that specific pin to prep itself to supply current. Once that setup finishes, we fall right into void loop. This is our infinite processing routine that runs forever, using digital write to actually pull the strings of our hardware.
When we send the high command via digital write, the microcontroller outputs the system's logical voltage. For an Arduino Uno, that means pushing a nominal 5 volts relative to ground. And when we command it low, it drops that output to exactly 0 volts. Just like that, our software logic is instantly transformed into electrical potential.
But here's the catch. If we just flip the voltage on and off instantly, our human eyes won't even be able to perceive it. And that is where the delay command comes in. By passing the number 1000 into the delay function, we are telling the internal instruction counter loop to just completely halt execution. It literally turns 1000 milliseconds of waiting into exactly 1 physical system second. During this precise window, all our state configurations remain totally immutable. The light stays on for a second, then stays off for a second.
Moving on to part 2, how LEDs actually work. Let's explore the microscopic magic of the p-n junction.
It is so vital to understand that the light generation happening here is nothing like an old incandescent light bulb. We aren't talking about standard thermal emission where a wire just gets super hot and glows. Instead, an LED is a specialized solid-state semiconductor. It utilizes a specific quantum mechanical process called electroluminescence, relying on nonlinear current voltage characteristics to release discrete quanta of light.
To really get this, we have to look at the p-n junction structure. Inside the LED, we have p-type doped semiconductors, which are packed full of empty positive charge carrier spaces called holes. Right next door is the n-type material, and that is highly concentrated with free electrons. Between them sits this default barrier called the depletion region. So when we push that 5 volts from our Arduino code, we are forward biasing the diode. We're applying an electromotive force that counteracts this default barrier. This energy essentially forces those highly concentrated free electrons to violently migrate across the junction right into the empty positive holes.
And the crucial point here is a process called recombination. As these energetic free electrons transition across the junction and drop into those empty holes, they are forced into a lower, much more stable configuration. Well, because energy cannot just be destroyed, that difference in energy is discharged outward as a packet of light, a photon. Literally every single time your Arduino blinks, you are triggering billions of these microscopic quantum drops.
But to actually build this working module on your desk, we need to physically identify our hardware to properly apply that force. If you look at an LED, you'll notice the legs aren't identical. The anode lead has a noticeably longer physical terminal length. This side absolutely must connect toward the higher electrical potential channel, the P side, which is our 5-volt Arduino pin. The cathode, on the other hand, is recognized by a shorter length, and if you look really closely at the plastic lens perimeter, there's a shaved flat notch edge directly molded into the casing. This N side hooks to the system common ground. Now we have our perfectly crafted C++ code, and we understand the quantum physics of our physical light. But before we connect the two directly,
We need part 3, preventing thermal runaway. Let's look at the critical role of the resistor.
You might be wondering right now, what happens if we just bypass any other components and blast the full 5 volts straight from digital pin 13 right into our LED's anode? I mean, it's just 5 volts, right? How bad could it really be?
Well, the answer is very bad, because an active semiconductor diode displays minimal internal forward resistance once you cross its voltage threshold. Failing to install a current-limiting resistor results in a direct short-circuit loop condition. Without any resistance to throttle the flow, the circuit enters instantaneous thermal runaway. The current spikes massively, and you will literally vaporize the microscopic internal wire bonds inside the LED casing. It will pop, and it's ruined forever. No way around it.
To resolve this high-stakes tension safely, we need a bit of math. Specifically, we rely on Ohm's law to calculate a static resistor that will sit in our circuit and act like a bottleneck, safely controlling our current throughput. This formula right here is our lifeline. Resistance equals the source voltage minus the forward voltage of the diode, with all of that divided by our target LED current.
Let's lock in the standard baseline values we need for our formula. First, our source voltage is 5.0 volts. That's the logic pin reference we pushed from our Arduino. Next is the forward voltage, the diode drop barrier. And actually, this changes based on the color of your LED. For red or yellow, it's typically around 2.0 volts, but for blue, it's higher, sitting around 3.3 volts. Finally, our LED current is our safe operating current threshold of 20 milliamps. But keep in mind, we must evaluate that as 0.02 amperes for the math to actually work out.
So, let's walk through a practical application using a standard red LED. Step 1, we substitute our known inputs. We take our 5.0 volt source, subtract the 2.0 volt forward drop of the red LED, and divide by 0.02 amps. Step 2 gives us our net loop drop target. This means the resistor needs to soak up exactly 3.0 volts of pressure at that specific current. So, step 3. 3.0 divided by 0.02 leaves us with a perfect target resistance of 150 ohms. If you use a 150 ohm resistor, your red LED will run at peak, perfectly safe efficiency.
But let's look at practical engineering for a second. If you open up a standard electronics starter kit, you're rarely going to find a 150 ohm resistor in there. The standard classification series usually features 220 ohm or 330 ohm resistors instead. And honestly, that's actually a great thing. Using a 220 or 330 ohm base starter kit resistor provides an engineered safety margin. It throttles the current just a tiny bit more, significantly increasing the protection factor for your components, and you get an absolutely negligible drop in the visual brightness of that electroluminescence we talked about earlier.
We have journeyed all the way from writing C++ commands that trigger microchip registers, down to the quantum jumps of electrons emitting photons, and zooming back out to the mathematical equations that balance the whole circuit safely. You now understand the complete anatomy of a blink. But I want to leave you with a final thought to really test this new knowledge. Now that you understand the full stack of code, quantum physics, and circuitry required for this working module, what happens if you decide you want a different color? Say you swap that red LED out for a blue one, which demands a much higher 3.3 volt forward drop just to jump its depletion region. How will you recalculate the perfect resistor to keep your brand new circuit safe? Think about the math, and until next time, keep exploring.